basically talk about is the formula tau equal to VQ over IT, these equations. And the things is here. We consider a being under a general loading like this one. And so the difference between this and the previous case, the previous chapter we just have the test on. Let me try to find my. In general, the beam is under any type of the loading like this one. It will have bending and also shear stress inside. So that is a big difference. That means, in general, in any cross section, and here I need to bring your attention is not only the bending, but also we have the transverse loading exists in any cross section. That is the difference. That is the difference between the pure bending. And again, our previous test is on the beam, is for the beam on the pure bending only. But here in these chapters, we have additional transverse loading, and that will make the whole things different. Okay. And that is due to this loading, we call it transverse loading, V. And that is due to this loading, and that will eventually give us this formula, tau equal to VQ over IT. And I believe you still remember this equation. And this equation, again, only one, but there's a lot of the meaning correctly, how to correctly apply the values for each term. That has a lot of things to say. Okay. And so that is the difference. And for this case, for this kind of the loading case, the bending and transverse loading have the relation. And for static, we know the dm, dx equal to v. And this is the relation. So basically the two won't be independent. They will be dependent. So usually we will, eventually for our formulation, we will try to relate m into v. So such that we can just have the cross-section be subject to v only. And that will give us this equation. Okay. And due to the existence or identification of the non-zero value of the v, right away we know that corresponding in the cross-section we will have the shear stress component. This one won't be zero. So not only we have the bending, we have the normal bending stress here, but also we will experience the shear stress. Okay, and before we kick into the detailed calculations, then that should be the phenomenon you bear in mind. And on the other side, for the previous chapters, if we only have the pure bending, so basically we will only have the normal stress and there's no shear. Okay, so that is the situations for this one. You just listen, okay, and right now until the point, I will write down on the blackboard for you to take notes. And this side represent is the portion of the whole entire cross-section. And already we know that we identified this should have existence of the shear stress on the cross-section. And that shear stress, and due to equilibrium, will be balanced with the existence of the shear stress on this side, and this side. Okay, everything. If we have identified one component here, then the shear stress on the other three sides must be there. Otherwise, the whole thing will move. But in this class, we talk about is static equilibrium. We won't talk about vibrations. Okay. So in this page, again, this portion is this side is a portion of the cross section. Identification of the shear stress component is due to our physical observation because transverse loading applied in this direction. This one is induced due to static equilibrium, and that is due to the existence of this one. If this one is zero, then the other three will be zero. So that come to this point. Again, we're back to our consideration of the beam on the general loading. And we consider a small portion, simply we cut a small cake into the beam like the things, okay? And this side is this is a little portion of the whole entire cross section. And we know in general the transverse loading will apply in this direction. And shear stress component will exist here. And due to the equilibrium, the shear stress will exist here as well. So that means if we would consider a wood laminate, so if this is a beam, the beam is made of the laminating the structure of a stack of the woods like this. And for this case, if we apply this an arbitrary bending, arbitrary loading, so for example here we have the bending, for example, we apply anything here. Okay. So at any cross sections we expose, we would have a free body diagram like this one. And per our analysis, and one more time, the shear stress will exist here if the transverse loading exists in that cross section, and that is generally true. So that means if we would pick up any cross section, you would expect that they should have the shear stress or shear force exist in each of the bonding phase. So that means if the bonding of the laminate is not that strong, cracking will appear throughout the whole interface. This case won't be seen if we have under pure bending. If we have a pure bending, we apply the same magnitude of the bending. For this scenario, they shouldn't have any transverse force or horizontal force there. For this case, under pure bending, the force in any horizontal plane is, let me use the symbol H, should be equal to 0. So this is the difference. This is the fundamental difference between the pure bending and the general, the bend on the general bending case. So here in general, you can see for this small portion and the small portion of the horizontal force, we call it eta H. So the whole piece will have, you expect that should have the whole H there. Okay. So before we again kick into the detailed calculation, right away you must know for the beam under any general loading conditions, they must have the transverse loading in general exist there. That transverse loading will induce the horizontal force there. Horizontal force will be working as to delaminate or crack the materials. Okay. The horizontal force won't exist in the case of the pure bending. So that is the most important concept, you have to pick it up. And with this in mind, then let me go back to the original, the general scenario. If this is under general the loading case, so that means in this cross section we expect the V is not 0, and then this V will induce the shear stress here, and that will again induce the shear stress here. That shear stress multiplied with corresponding cross-sectional area will give us the force. So that means here, for example, in this cross-section, we would expect the force H. And let me put into three-dimensional drawing. So here, for example, here the three-dimensional case will be like this one. Let me use this. So this will be the three-dimensional drawing of this one. So H is existing, and due to the existence of transverse loading, H existing in this plane. From the 2D view, we see is a line, but from 3D view, H actually acting on here. Okay.
So would H differ with the depth?
H, if the depth, yes, H is different from the depth wise. And for this stuff, let me say this cross-sectional area is equal to A. Then we'll be able to calculate H divided by A. This gives us, this H is a force, divided by area is a stress. What kind of a stress? Shearing or normal stress? Shearing, because H is a force parallel to that cross-section. So this one we obtained is the shear stress. Because we divide by whole area, so basically we ignore the little variations from point to point in that area. So here we talk about here is the average stress. Are we good? That's it. And then probably we can take off for 5 lecture hours and then coming back to take the test 3. That's it. That is for everything.
That's everything.
That's
for
for
this
everything.
section.
That's for everything. And then the detail is how you simply implement the calculation of the H, and then going to here. Okay, so this one basically, if you do the calculation symbolically, this one basically leading to that area, that equation. This equation is nothing less, nothing more, just be this concept. So I would rather to talk about the concepts first, and then before we go to the detailed calculation. Okay, so you know the meaning of the things here. Okay, and for example, say let me pick up the corner cube here. Okay, so let me enlarge the corner cube. So this is the portion of the cross section. Okay, so here this one is a portion of the cross section. Hopefully you know what I mean here. And now we've been calculated this tau average. It's been calculated at the bottom side. So here let me label it. Tau average is here. Okay, this is our tau average, and that one equal to H divided by A. So again, one more time. Go to this case, the equilibrium. If we would know the shear stress component on one side, the other 3 sides must be existing. So the other 3 sides, this one should be, the arrow must be converged to the same age. So that is here. So this is the component of the shear stress on the cross section. So again, let me draw the cross section here. For example, the cross section will be like this.